Perfect. We can start. You are muted. You are muted.
I'm sorry. Good afternoon and a warm welcome to everyone. On behalf of Nehru Planetarium, Nehru Memorial Museum and Library, I welcome you all for yet another online session with Professor Priya Hassan. Planetarium welcome you, ma'am, once again. Today we are here for the talk and to understand more about the much exciting episode which was in the buzz globally. This was the Double Asteroid Redirection Test, also popularly known as DART mission by NASA. DART is a NASA space mission aimed at testing a method of planetary defense against Earth's near object. This mission has created the revolution in space science by successfully changing the trajectory of the asteroid, marking the first time humanity internationally changed the motion of a celestial object in space. Today, we are here honored to host once again Dr. Priya Hassan to give more understanding on this exciting mission. About Priya ma'am, would like to share that in the past she went to USSR to pursue her integrated masters in physics at the Maslow State University, Russia. She did her PhD in astronomy in Osmania University, Hyderabad in 2004. She did an Indo-French postdoctoral research project at Inter-University Center of Astronomy and Astrophysics, Pune, and worked as DST scientist in Osmania University from 2004 to 2006 and 2006 to 2009. Sorry. She taught at Mukafum Jahan College of Engineering and Technology, Hyderabad, 2010 to 15, and later joined Maulana Azad National Urdu University, Hyderabad in 2015 to till now. Planetarium is very excited to host you once again, ma'am. And thank you for suggesting this topic because this is much needed. One of the topic I think which need more clarity and understanding. And I think all the young minds, space enthusiasts are really excited to know about this.
So thanks so much. Thanks so much. Thanks, Prerna. Thanks so much for having me with you. And let me share my screen.
Meanwhile, ma'am is sharing her screen. I request everyone they can post their relative questions and doubt in the chat box, and later we'll be taking them for the clarity. So you can post in the chat box. Yes,
Uh,
ma'am.
uh, yeah. So can you see my window? I hope you can see my window.
Yes, yes,
Yeah.
yes.
So thanks a lot. Thanks, Prerna, for having me, and thanks for getting me here. And today I'll be talking about something which has been a lot in the news, which is the DART mission. So I've titled it Throwing Darts at Asteroids, which is in a way what we're going to talk about, or what do we mean by throwing darts at asteroids? And in what way is this part of NASA's planetary defense mission? Right. So we'll come to that in a bit. Yeah. So what exactly was the DART mission? Now, the DART mission was it was the first test in principle. It's the world's first test of a kinetic impact mitigation technique using a spacecraft to deflect an asteroid. Now, I will describe what all these things mean in a short while from now, but this isn't the crux of what it means. So it was called the double asteroid redirection test. And so let us first start off with trying to understand is what are asteroids and why are asteroids important to us? Now, most of you are maybe aware of the Cretaceous Paleogene extinction event, which is basically the event which got the dinosaurs extinct, which took place about 65 million years ago. And what we know is actually there was an impact of a massive asteroid, which had a size of about 10 to 15 kilometers, which impacted the Earth. And this basically what it did is because of the impact, you see, the asteroid is not so big, it's just 10 to 15 kilometers. But because of this, the amount of dust which got onto the atmosphere, that created a kind of a blanket around the planet. And due to that blanket, the plant life on the planet could no longer do the photosynthesis, due to which the life forms which depended on plant life could not get enough of food for them, and then it went on to the food cycle, in the sense the ones who were then eating them did not have their food, and in that case you have the extinction taking place in that kind of a way. So it's actually a small asteroid, 10 to 15 kilometers, but that's what did the job, what did it. And we have enough of proof that this is what happened, because we actually have layers, sedimentary layers made up of a metal called iridium, which is common in asteroids. And also there was a discovery of a 180-kilometer crater in the Gulf of Mexico's Yucatan Peninsula, which was probably the result of this event. So we quite well understand this event, and this is what actually happened. Now, because we know that asteroids pose a threat to life on Earth, June 30th is actually celebrated as the Asteroid Day by the UN. And basically, this is a day to build up planet's public awareness of the risk of asteroid impacts. It's observed annually, and it commemorates the asteroid impact which took place in Tunguska. Tunguska is in Russia, and you can see over here, this is the clearance which was more than 100 years ago, and you can see even to date the result of that event. You can see the result even after 100 years, you have this effect in that region where the asteroid actually fell. Now, what are asteroids, and why are they to fear of? So, in principle, every day the Earth is bombarded with more than 100 tons of dust and sand-sized particles. This is what we call shooting stars. If you lie down and look at the sky in the night, you will see these streaks, of light coming up in the sky, and they are essentially meteors which get into our atmosphere, and because of the friction in the atmosphere, they immediately evaporated and they burn off at higher levels of the atmosphere. So they actually don't even fall on the Earth; they just get burnt off over there, right? So this is something which happens on a daily basis to us. But about once in a year, you could have a larger size asteroid, which is about the size of a car, which could actually create a fireball up there. It still is not harmful. But about every 2,000 years or so, you could have a meteorite which is the size of a football field, and that can cause significant damage to the area. Locally to the area where it falls in. And then once in a few million years, you could have something like the event which wiped out the dinosaurs, which could actually leave very low, strong, a strong impact on the Earth. Now, so space rocks, which are smaller than about 25 meters, they burn up in the atmosphere, nothing much to worry. If they are more than 25 meters, but smaller than 1 kilometer, it would just be to the local area. But if it's larger than 1 or 2 kilometers, that could actually have worldwide effects, and you could have a problem with that. Now, there are a whole bunch of asteroids which are quite close to us. They're potentially hazardous asteroids. But the main belt where asteroids lie is between the belt between Mars and Jupiter. But these are very large asteroids, size of even 940 kilometers, 1,000 kilometers. But they're reasonably far away from us and not much of a threat to us. But where do these asteroids that we're talking about, where do they come from? What are they, and where do they come from? Let's ask that question. So a long, long time ago, this is the time of formation of the solar system. You know that the sun formed from a protoplanetary nebula, right? And this protoplanetary nebula, as it was collapsing with its own weight, you can see that while the sun was forming in the center, you have these regions which are forming around it, and within these you have planets forming at different orbits, right? And they form orbits. But and the star is born in the center. You have these orbits over here where you have planets forming, right? But while these planets form, there is dust and gas between them, which is some kind of debris which did not end up in a planet. And that's this kind of debris which is essentially what is these asteroids, right? So it's basically debris which happened from the planet formation process from the time of the formation of the solar system, right? So the asteroids belong to that period of the formation of the solar system. And so our solar system, if you see the sun you have in the center, you have all the planets, Mercury, Venus, Earth, Mars. And then between Mars and Jupiter, you have what is called the asteroid belt. Probably there was a planet which did not form over there because of the strong gravitational force of Jupiter, or it was that's the asteroid belt, or it was a planet which broke. And you also have another region outside over here, outside Neptune's orbit, and you have the Oort cloud, and this is all debris. So the Kuiper belt and the Oort cloud, this is all debris from the time of formation of the solar system, right? And therefore, if you had to actually look at the amount of asteroids we had, like I mentioned, you have the asteroid belt between Mars and Jupiter. You also want to have the Trojan asteroids. These lie at what are called the Lagrange points. These are the points where the gravitational force is balanced, and hence you have a large number of them. And so you have these things, and once in a while you do have these things which actually come into the solar system. Now Mars has two satellites, which is Phobos and Deimos, and most probably these were also asteroids which were captured by Mars while they were orbiting. So if you actually have a look at the known asteroids, now we have better observing facilities which we try to monitor asteroids. You can actually see that if you see the number of asteroids that were known, this is between 99 and 2018. This is old, slightly old, but you can see that because of our improved techniques, we have been able to detect a very, very large number of asteroids. And you can see them over here. So there are the known near-Earth asteroids. You can see as the time has increased, the number of asteroids which we know and which are catalogued, for which we know their orbits and their sizes, etc., has been growing with time. So now we have a very good consensus of of a good number of asteroids within our solar system, right? So that's the about information. Okay. So, like we mentioned, the asteroids basically formed. They were leftovers from the formation of our solar system 4.6 billion years ago. And understanding how, so in principle, asteroids are interesting objects because if one is studying the formation of the solar system, then you can actually see how the solar system evolved. And there is actually the NICE model, which is the standard model to understand the formation of the solar system, in which basically we know that the gas giants were much closer to the sun, and then they gradually moved away to their present orbits. And that's when they basically sent asteroids, kind of spread them along the system, and you have them lying in different places. Now, what are these asteroids like? They're essentially irregularly shaped. They have boulder-like shapes. They could be not all of them are spherical. Most of them have kind of uneven shapes. Some of them have craters on them. They have pits on them. And for example, there is a very well-known asteroid called Vesta. It has a crater which is about 460 kilometers in diameter. And many of these asteroids are covered with dust. They revolve around the sun in elliptical orbits. They also rotate. Sometimes it's almost tumbling motion, so they don't have very ordered things. Some of them are binaries. You could have double asteroids and or even triple asteroid systems. The average temperature on the surface of an asteroid is about minus 100 degrees Fahrenheit. And they've actually stayed unchanged for billions of years. So they are excellent fossil records of the early solar system. So if we want to know what the early solar system was like, asteroids are the right hosts of this information of what the early solar system was like. And like I mentioned, they come in a variety of shapes and sizes, solids, etc., various things. There are different types of asteroids based on their composition. There's the C type or the carbonaceous asteroids. So they basically consist of clay, stony silicate rocks. There are S type asteroids, which are silica. There is M type, the metallic ones. And then there's some which are made up of even rare materials, volcanic crust, etc. Right? Now, minor planets, when we talk about minor planets, they include asteroids, near-Earth objects, Mars crossers. They are categorized into these various categories: main belt asteroids, Jupiter Trojans, etc. And there are millions of asteroids ranging in size from hundreds of miles to several feet across, right? Uh, but in total, the mass of all the asteroids is less than that of the moon, right? So it's still a smaller mass. And like I mentioned earlier, why are asteroids important to study? First of all, like I mentioned, they have fossil records of the nebular phase of our solar system, what was in the early solar system. They are bearers, they actually hold carbon-based materials, or like I'll come to that in a short while about water. One of the theories of water on the Earth is that it came through an asteroid. And they also need to be obviously monitored as they could cause mass extinction of life on the Earth, like it happened in the case of the dinosaurs. And then there's also now interest in asteroids in terms of mining. You could have asteroids which have very rare metals, their materials in it, which could be very interesting for mining purposes. So another way of classifying asteroids in the classification Atira, Aten, Apollo, Amor is based on its on its orbits. So the Amor asteroids, they have orbits that approach the Earth's path but remain between Earth and Mars. The Apollo asteroids, they have Earth crossing orbits but spend most of their time outside the planet's path. 18 asteroids, they cross the Earth's orbit but spend most of their time inside the Earth's orbit. Asteroids are near the asteroids whose orbits are contained within the Earth's orbit. So these are the important ones which we need to monitor when we are trying to look for potential disaster getting things, right? And as of October 2021, scientists have discovered more than 27,000 near Earth asteroids, of which about less than 10,000 of them have diameters larger than 500 feet. Okay. Now, how do we basically find asteroids? How do we find them? Now, to be surprising, this is more than 200 years ago. While making a star map, there was an Italian astronomer called Gispiasi, and he actually discovered the first, and that is the largest asteroid known to us, called Ceres. It orbits between Mars and Jupiter. And today, Ceres is actually classified like a dwarf planet. It accounts for a quarter of the mass of all the known asteroids in the asteroid belt. And since then, since about 2000, NASA has actually spearheaded a campaign to identify and track near Earth asteroids. So there are various NASA missions, which are constantly monitoring the sky and looking for asteroids. I'll show you in a bit what an asteroid looked like and how can you identify an asteroid in the sky. I'll show that to you. So if you actually see the spread of asteroids, you see that the number of asteroids as the diameter increases, the number of them, obviously, you can see that the large number of them have these kind of diameters, and that's the kind of spread which you have with sizes of asteroids. If you look at the largest asteroids we know, the largest one is Ceres, which has it has an orbital radius of 2.77, while itself it has a diameter about this. See, it's not exactly a sphere, right? So you can see it's more like a cuboid kind of a shape, 964, 964, 892. Vesta is also a large asteroid, which has a size of about this. Pallas Hygiea. So you can see that these are the masses in proportion of Ceres and the densities, which you can see, the rotation periods, right? Uh, Now we come to the very important question that can asteroids hit the Earth? The answer is obviously yes. We know that that has actually happened. It keeps happening. And ever since the Earth formed, they have continuously done that. But for an asteroid to be capable of global disaster, then it have been more than 400 meters wide. And in that case, these kind of asteroids can actually cause a global disaster. Now, those ones are called the near Earth asteroids. Now, an asteroid is called a near Earth asteroid or an NEA if its trajectory brings it to within 1.3 astronomical units from the Sun and hence within zero point 0.3 astronomical units of the Earth's orbit. Now, one astronomical unit is the distance between the Sun and the Earth, which is 150 million kilometers. So, zero point 0.3 of that is the distance at which it would be this thing. And of these near Earth asteroids, there are some of them which are tagged as potentially hazardous asteroids or the PHAs, whose orbit comes within 0.05 astronomical units, or about 7.5 million kilometers. Okay, if it comes within that distance, then we call them as potentially hazardous asteroids, right? So the largest known one was Tutatis, and that's the details about it. Now, many of you all may have actually seen it. If you all have not seen, please do watch this movie on Netflix, which is called Don't Look Up. And Don't Look Up is actually a beautiful movie which basically reflects upon, is the human race actually prepared for an asteroid impact, right? If it were to take place. So you have a PhD student while doing her routine observations with the Subaru telescopes, she discovers an asteroid, which she reports to her supervisor, and together they calculate the orbit of this asteroid. So they realize that this asteroid is going to hit the Earth, right, in 6 months. And when they go to the president and they try to tell the media, they try to tell people things about it, the movie is a satire. It's almost a comedy on how badly we are prepared for such a thing, right? So part of the purpose of this talk, as well as the dark mission, is basically in building our awareness and actually preparing ourselves for such an event if it were to occur, right? So we'll actually see how are we preparing ourselves. Now, like we said, many asteroids have actually hit the Earth at various points. In 2013, which is like barely 10 years ago, as an asteroid actually, again, it hit in Russia, in a place called Chelyabinsk. And what it did is when it hit, it created a shock wave. You will actually see on YouTube, you can see videos of that. It created a shock wave which actually crushed glass. And you had about 1,200 people who actually were injured. And this was just a rock which was only 20 meters across, right? Not very big. But this was the kind of impact it had in that city. And that's when people became even more and more aware that it is high time we actually plan something to protect ourselves, right? Now, a meteorite, just to clear this thing, an asteroid is out there in space. If it comes and falls on the Earth, then it is called a meteorite. If it is still up in the sky, it's a meteor. But if it hits the Earth, we call it a meteorite, right? And we know that there have been various meteorites which have hit the Earth. Basically, you identify them based on their composition. They have very stark different composition from material which is there on the Earth. And one of the things which we need to consider a blessing, so like we needn't think of these impact as only disaster events. One of the very standard theories of how the Earth actually got water is actually from an asteroid, right? So the Earth, when it formed, it was dry and barren. And it is expected that because of this impact, right, which took place with an asteroid which actually had water on it, right, that actually created the circumstances for life to evolve onto the planet, right? And otherwise, such an event not taken place, then probably life on the planet would have not been possible, right? So there are various asteroids which also have water. For example, in 2009, another asteroid was found, 24 Themis, which also has water on it. And like I mentioned, most probably even the water on Earth came in from an asteroid. Now let's go back to the ones that we need to protect the Earth from. So if we want to protect the Earth from asteroids, how do we do it? So for every known asteroid, obviously there are many which have not been spotted, right? So if asteroids do close flyby, right, then you can actually find them through radar, right? So in 2017, there was an asteroid which was actually found. It was at a distance about 7 million kilometers, and it was actually detected using a radar. And with the radar, they got information about its shape and craters on it, moons of it, etc. And so, in principle, radars are actually a good technique to find asteroids. Other than that, there is actually a site which is called the Center for Near Earth Object Studies, where you'll find a lot of information about near Earth objects, which has various things. For example, of those near Earth objects, what are their orbits, what are their closed approaches, what's the impact risk, what is the planetary defense, this thing, etc. There's also what is called the which is basically this is done by the NASA Planetary Defense Coordination Office. There's also the AIDA, the Asteroid Impact and Deflection Assessment Collaboration. ESA has also been active in this, as well as John Hopkins, etc. So the important catch in this is extraordinary rapid response. So first thing is you need to detect it, and after that you can do some response, right? Now, so this is the Planetary Defense Coordination Office. You can go to the website and you'll actually see there are various observations and lots of data over here sitting about these kind of objects and where are they, etc. Right? So these are actually being cataloged. Now the question is, how can we save the Earth from such a planetary defense? So I'll just show you some of the possible cases which people gave. For example, there was this thing which is called the slice and dice technique. So basically, it means that if you have an asteroid, you place small rockets on the surface, right? And that would kind of slice and dice the asteroid. So you kind of break it up and you make it into 100 pieces. And those pieces, once they are small enough that they will just burn in the upper atmosphere. If you remember, I told you that if the asteroid is too small, it will just burn in the upper atmosphere and that's the end. So what you need to do is you just slice it and dice it in some way, and you do this kind of a thing, right? Another, very innovative idea was about spray painting. We'll come to that in a minute, in a short while. That actually, if the reflectivity of an asteroid is changed, it can actually deflect its orbit. This is called the Yarkovsky effect. So, if you actually had an asteroid and you spray paint it with something with different properties of albedo or different reflective properties, then the darker regions obviously reflect less, lighter regions reflect more, and the Yarkovsky effect will actually deflect the asteroid. The asteroid will actually move into a different path, and in that way, you can actually move the asteroid away from the Earth. So it's basically by painting them. Some of the ideas which is used in science fiction movies, Star Wars and Star Trek, This was a gravity tractor. So you actually get something which is really with a strong gravitational force, and that gravitational tug, right, can actually go there, accompany the asteroid for a while, and actually literally pull it away, right? So it's literally like you had a handheld thing which pulls it away and moves it away, the tractor beam, right? There's also the ion propulsion method in which you can use charged or electrified molecules to actually deflect this thing. And was actually tried out. So there was a NASA spacecraft called Dawn. And in Dawn, what they did is they visited two space rocks, Ceres and Vesta, and they actually tried to do this ion propulsion method, which I am this thing. Another one is laser ablation. You have a laser beam, you throw laser beams onto this, and you in that way you kind of break the asteroid. So spacecrafts often they could be CubeSats or something. They could surround the asteroid, laser it, and actually kill it. Right. There's also what is called the asteroid theta, which is actually you put a net-like thing. Right. This is actually like a net-like thing, and with that net-like thing, which is called the weightless rendezvous and net grapple, you can actually pull this thing and move it to another path. Basically, you need to deflect it to another path, right? So it doesn't this thing. And of all these which options which I gave you, the most plausible option is the one which is called the kinetic impactor. So in the kinetic impactor, what happens is you impact this thing with a non destructive projectile, hit it in such a way that it changes its orbit. So the thing is, you actually don't need to break the asteroid. All you need to do is you just need to change its orbit. So if you have an asteroid which you think is a threat and you impact it, can you just push it away and stop it from coming to the Earth? And that's exactly what the DART mission did. It was the first kinetic impactor to do that, right? So I'll just sum it up. There are different ways of avoiding a collision with the asteroid. Like I mentioned, first one is the one in which you burst it off, which is also there in a few movies, where you have a nuclear explosion. You break it into smaller pieces so that it distinguishes. You could have a gravity tractor which kind of drags it off. You actually, and the third one is the method which is what we're doing for DART, where you actually push, just give a slight push to the asteroid so that you change its orbit. And if you change its orbit, it's not going to impact onto the Earth, right? So in that way, you can save the Earth, right? But obviously, to do this, we need to know what are these asteroids made of, because if we want to deflect them, what can be done to deflect them? Because we need to know how much of an impact we need to do so that we can push it away or break it into pieces. We need to know what is the composition, right? And therefore, there were various missions sent to asteroids to actually study asteroids, right? Study their composition to figure out how could we actually do this thing of, deflecting these asteroids. So the earliest one amongst the earliest mission was a spacecraft called Galileo, 1991. So like 31 years ago, which was the first moon to orbit an asteroid in 94. Okay. And in okay. And in 2001, there was another spacecraft called NEAR, which is NASA spacecraft. And what it actually did is it studied the near Earth asteroid Eros for more than a year. And it tried to land on it. It wasn't designed for landing, but it was the first one to actually land on this thing. After that, in 2006, Japan had a Hayabusa mission, which was the first spacecraft to land and take off on an asteroid. Okay, so there was an asteroid called Itokawa on which it actually landed, and it returned a small amount of asteroid material to the Earth in 2010. And then, like I mentioned earlier to you, the Dawn mission actually went to the asteroid Vesta. It was launched in 2007, landed there in 2011, and it actually it visited both these asteroids, Vesta and Ceres, and kind of studied their composition. Right. The first attempt of not exactly doing a kinetic impact, but a kind of an impact was the Deep Impact spacecraft. So in 2005, NASA actually launched this Deep Impact spacecraft. What it did is it shot a 370 kg copper impactor onto a comet. Okay. But the purpose of this was basically to study the composition of comets. Comets are also very interesting objects because, if you may have heard of, one of the theories of the origin of life is that comets could be carrying amino acids or life and transferring it all around the universe, right? So a comet can act like this super refrigerator which can carry life and life building material on it in this frozen form. And then when it lands onto a surface where there is life, it's good for life, then in that case it can actually lead to life, right? So therefore, comets are also very interesting, and the purpose of the Deep Impact mission more was to study the composition of comets. So it impacted this comet, but what the problem was that once the impact took place, there was so much of gas and dust that the images which were taken by deep impact of the crater, they could hardly be seen. There was a very small change in the orbit, barely 10 centimeters, small change in the velocity, but that's basically because this was a very large comet, and therefore it could not affect it, that much. And then another mission was done in 2011 called Stardust, and Stardust did a follow up of that previous mission, which is the Deep Impact mission. And it basically, this impact which took place in 2005, it finally could check out what was the effect of that impact in 2011. And it actually found a scar, a 150-meter diameter scar on the comet, which was the result of that impact which had taken place earlier. Now, Japan also did another mission. We spoke about Hayabusa 1. There was also Hayabusa 2. NASA also did an Osiris Rex. This is to study the asteroid Bennu. And Hayabusa 2, you can see, it was launched in 2018 to 2019. And basically, what it did is that it studied an asteroid called Ryugu, and it actually collected samples, sent them back to Earth for analysis. And so it had a set of landers, penetrators, etc., which did that. Osiris Rex, this is another spacecraft which recently was launched in 2016. And it reached this other asteroid called Bennu, and it will return the sample in this year. It actually drilled a hole and got the material, which is being sent back to the Earth. Now, in continuation to this, you had the DART mission. The DART mission was a continuation of this. It was launched in November 2021. And what it was trying to do is again test kinetic impact. Can we actually push an asteroid in such a way that its path does not get into the path, doesn't, it avoids this impact of an asteroid, right? Can we actually do that, right? That was the question. And that's what we were trying to check with that mission, right? So what happened is that now what was the impact they could do? So there's this very interesting asteroid called Didymos, which has a satellite called Dimorphos. Okay, now Didymos is is roughly 5 billion kg in mass. So if you remember the Temple case, in Temple case also the comet was very large. So when they impacted it, it did not create much of an effect. Now Dimorphos actually has a satellite called Didymos, and Didymos has a mass which is much lesser. Sorry, the larger one is 540 million kilometers. This is 5 billion. It's much lesser in mass, and it goes around this thing. And this was the good potential target to hit, to check for kinetic impactor. So what was the experiment? The experiment was we launched this mission in November 2021. It reached this asteroid Dimorphos. This is a binary, this thing. It reached there in September 26th. And then what was done is that it intentionally crashed. It crashed into Dimorphos, which is the satellite, at a speed of about 6.1 kilometers per second. And the idea was to check whether this can create enough of an impact that it can change the orbit of this satellite, which is Dimorphos. Okay, so this was actually done last year in September 26, 2022. So if you can see over here, this is the video. In a galaxy. So what you can see is here you have the mission. This is the DART mission. And like you can see, this is the DART mission, and it's on its way to Dimorphos. And here you have the thing. And what happens is it's supposed to impact it. And while the impact took place, so this is the impact which is to take place, and it hit it, and that is what we are actually measuring. What is the effect of this impact, right, which is taking place? So so what happened is that, so in principle, this is the first attempt to actually doing this kinetic impactor. And these are other details about it, that this was launched by a SpaceX rocket, etc. But the basic idea was to check what happens. So on this same mission, there was also another CubeSat called Lycia Cube, and Lycia Cube is in principle the camera, right? So before the impact took place, Lycia Cube separated from DART so that it could actually take images of the impact, so that we could actually see what happened with the impact, right? So here's the DART mission. You can see it. Here you have Dimorphos and Didymos, and this is the original orbit. And now that when we impact it with the dark this thing, see, that's why you need a binary thing, because with the binary it's very easy for us to actually check the difference in the orbit. If it was just a field asteroid, then there'd be no reference point, you won't be able to identify. Now here's the dart comes and hits it. Lycia cube is separated to take the images. There's an impact which takes place. Lycia takes the images and sends it back to the earth, and now this thing will have a new orbit, right? And the idea is to check what is the new orbit, what is the change in the energy of this thing, and to basically estimate how much can we deflect an asteroid which is actually coming. So it's just like giving it a dart, giving it a nudge, giving it a push, pushing it away so it does not come and impact the earth. That is the basic purpose, right? Uh, so it's in principle, it is what you could call a not so gentle nudge to this. So Dimorphos is hit by this, you have a new orbit, and we try to check out what is the difference in the orbit. Now, like I said, this kind of a binary system is the ideal system in which we can do such measurements, because if you had an isolated asteroid, it would be very difficult to check what are the difference in energy, and what is the difference in the motion. But in this case, you already had a binary, this thing, you had Dimorphos already going around Didymos in a particular orbit. With this, now you can actually check what is the new orbit, and you can estimate what is the total energetics of the system, right? How much of energy has been given out by the system, and in what way can you actually see it. So what was done is that various researchers, while the impact took place, various ground-based space-based observatories, telescopes, actually tried to monitor the event, right? So, like I said, this happened on September 26th, and after that, you had a whole lot of these other telescopes, missions, which were actually observing to actually check what is happening, how well has it done its job. I also mentioned to you earlier something which is called the Yarkovsky effect, that in the case of all these asteroids, since they have a certain albedo, right, a certain reflectivity, so when the sunlight falls on them, some part of it gets hot and some part of it gets cold. And because of that, there's a seasonal variation between temperature variation on the surface of an asteroid, right? Some parts could be hotter and some parts could be colder, due to which the orbits of these asteroids are not very well defined, right? So for asteroids, the orbit can slightly change in different seasons, right? So therefore, when one is trying to check out the orbits of Dimorphos and Didymos, one has to also keep this into mind to see that how much of this difference in orbit has basically caused because of the Yarkovsky effect, right? And how is that actually changing the orbit of the asteroid, right? So Lycia cube, like I mentioned to you earlier, this is an Italian CubeSat which is there on the DART mission. It's basically a camera, right? Its job is basically to shoot the whole event, right? So while the impact was to take place, you had Lycia cube which actually separated from the mission, right? So it's separated here. You can see this is it's separated. This is the camera. And while the impact took place, it actually shot videos of the impact, and it flight by from there to actually see what was the effect that took place of the impact on the thing, right? So that has been actually observed by Lycia cube. That's the job of Lycia cube. Now, on Earth-based, one of the these things which is called the Asteroid Terrestrial Impact Last Alert System, which is called ATLAS, they actually have a collaboration with the University of Hawaii, and they basically detect rogue space rocks. Not just this, their job is to all the time monitor all these space rocks and see if any of these are in a potential condition to actually fall on the Earth, impact them. So here I'll show you an image which is got from Atlas telescope. This is in Hawaii of the same impact, right? So you can see the impact is taking place over here. This is the thing going. And you can see with the impact, so much of dust. Remember, in the other cases also, I told you that when these things are impacted, a lot of dust comes out into the from that thing. And therefore, now when we're trying to study these orbits, it's very difficult because the problem is a lot of the angular momentum is taken away in that dust, right? So if you are trying to measure the energetics, how much of energy is being released, how much of is being transferred, etc., it's a little tricky job because you also need to monitor that dust and how much of angular momentum has gone away with the dust, right? So the Atlas telescopes in Hawaii, they were the ones who were monitoring this impact. And while the probe was traveling at 14,000 miles per hour when it hit it, about 30 ground-based telescopes have observed it in optical and radio frequencies. So that was the one which I showed you, which was the one which we had with, this is Atlas, right? This is Hawaii. So this is with Hawaii. You can see that this is the kind of impact we had, right? And you can see that even with James Webb was also used to check this impact. And if you see over here that this is an animation made up of images from the James Webb, so you can see that the amount of material which is being thrown out from this thing, right? So there's extreme brightening which you can see which is taking place, and that's basically because of the impact and the amount of material which was thrown out. So this is a James Webb image. Let us recollect that James Webb basically works in the infrared, so it's basically showing you the kind of infrared emission that you are getting from this system, right? And that's the James Webb image. It was also observed by Hubble. This is an animated GIF image from Hubble, this thing. It's about 22 minutes after the impact to 8.2 hours. And again, you can see that the brightness has increased by almost 3 times and after the impact. And that's the effect of the impact over here. So why do we need to observe it with Hubble space as well as James Webb? So basically, we want to know about the surface of Dimorphos because we want to know what actually happened with the impact. We want to know how much material was ejected by the collision. And we are aware that James Webb basically observes in the near infrared. Hubble does it in the optical. And therefore, different material, right? Different kinds of material will emit more in optical or in infrared, right? So with the colder dust, you'll be able to see that with the infrared, which is in James Webb, while the optical part, you'll be able to see it with the Hubble Space Telescope, right? And that is the basic idea of seeing it with both these telescopes so that you can make an estimate of, you can have actually see what was the material which was ejected and how fast was it ejected. And by looking at it in different wavelengths, you will get much more information. One can actually study the distribution of particle sizes depending upon the expansion of the dust cloud and see whatever kind of material it actually tried to throw, right? So the basic question is how can the kinetic impact actually modify a asteroid's orbit? That is our main purpose because we want to know whether this method can be effectively used for our purpose. That is to modify the orbit of an asteroid if you know an asteroid is coming onto you, right? Now, how are these measurements made? It's a very difficult measurement. So, what you actually have is while you have this, you have the sun and you have Didymos's shadow, if you observe it, you'll see that you'll get a light curve. This is called a light curve. That means there's a difference in brightness. So, depending upon the position which you have of Didymos, you will get this difference in brightness, right? And this difference in brightness or this curve, light curve, is basically used to study the orbit which is there, right? Now, this one actually had an orbit of about nearly 12 hours, right? 11 hours, 52 minutes, something like that. And it actually shortened by this impact. We know that the orbit has actually got shortened by 32 minutes, right? So if you were to see these dips, you'll see they've got shifted by 32 minutes. When actually, when the experiment was done, it was predicted and expected that this will cause a change of about 1 minute, right? But with the data which we have, we know it's caused a much larger change, 32 minutes. So essentially, what it means is that after the dart impact, what you basically have to do is monitor the light curves which you're going to get from these, right? And use those light curves to actually get these things. So it was 11 hours, 55 minutes, the original orbit. And now with these observations, we can see that the new orbit is about 11 hours, 23 minutes, right? It's gone reduced by 32 minutes, right? So that is the approximate change in the orbit which we are getting because of the effect of this impact, right? And Lucy. So now this is one probe, but there are still more probes which are still studying asteroids. There is the Lucy probe, which is um, which is on a which is actually going to be studying 8 different asteroids, which is basically it has already been launched. 7 Jupiter Trojans asteroids which share Jupiter's orbit around the sun, and there'll be flyby encounters, etc. So the Lucy mission is something like this. It has been launched in October 2021, and then it's going to loop around like this and observe these L1 Trojans and L2, these two different Trojans. Actually, these Trojans are at L4 and L5, and it's going to actually visit both these things and cycling between them every 6 years to actually observe them, right? There's also another mission which is being planned probably this year, which is called the Psyche mission, which will also explore the origin of planetary cores by studying metallic asteroids of the same. The asteroid is called Psyche. It's going to basically observe that one. Another interesting thing about asteroids is, can we actually mine asteroids, right? So if the movie I spoke to you about, Don't Look Up, the Netflix film which I spoke to you about, which talks about a possible asteroid impact. In that story, what has been shown is that the president is actually advised by this mega businessman, who actually advises her that the asteroid should be actually mined because it has various minerals on it. So while the president is not so worried about the impact of the asteroid, the president is more concerned about the monetary advantage that they can get from the asteroid, right? So there are many ideas of people have of actually mining asteroids, because they could have a lot of important minerals, material on them, and then they could also have water, right, which is useful for us too. So there is actually a whole bunch of companies, startups, which have come up based on actually thinking of asteroid mining. It's something like the modern day gold rush, where people are thinking that this is the way to actually go and actually look for example, platinum rich asteroids, or various rare metal asteroids which can be used effectively to actually be mined, right? But that's something of the future. We talk of this thing. Now let's get back to our thing. So now we saw the DART mission, which was quite successful in actually doing this kinetic impactor. But the important thing is that you need to know where is the asteroid, right? So how can you actually detect asteroids, right? Now the asteroids are basically detected by their shift. By taking, so you basically have to take successive images of a patch of the sky, and you'll see a shift. So I'll show you this, for example. In a minute, I'll show you in a minute or two. So there is what is called the NEO-WISE mission. There was the WISE mission, which is now being used as the NEO-WISE mission. This basically observes in the infrared, and it basically looks at these near-Earth objects and tries to catalogs them, observes them in 4 infrared wavelength bands, so that it actually monitors them well, right? There's also the Mythnios MIT in Hawaii, this thing, which is actually trying to do a spectroscopic survey of these near Earth objects, essentially to study their composition and to see what can be done if one has to do something about detecting them. And there are many projects which actually work on near Earth object detection, on actually detecting them, right? I'll show you in a minute or two how do they get detected, but there are various ones. So there's what I told you, the planetary defense, asteroid hunters. So what people have to do is you observe, and if you detect a suspicious object which you think is an asteroid, you can actually report it to the Minor Planet Center, and the Minor Planet Center will do further observations, plan further studies, and this thing whether your detection, number one, is it's an asteroid, and you could actually then have the pleasure of naming the asteroid on yourself, name it yourself, if you actually detect one. So there is the Catalina Sky Survey. There's the PAN-STY survey, which is called Panoramic Survey Telescope. There's the Atlas Survey, the Linear Survey. All these are surveys which basically scan the sky looking for asteroids. And then once you detect one, then you actually have follow-up missions, which are for follow-up, right? These things which are done by University of Arizona Space Watch, there's the Las Cumbres Observatory, the Magdalena Ridge Observatory, various observatories, as well as radar projects, which actually try to monitor and check on these objects. Canada also launched a satellite called the NEOSAT, and the NEOSAT essentially does the same job of basically detecting asteroids, right? But for example, this satellite, it could not detect the one that fell on Chelyabinsk, okay, because it was only 15 meters across, right, 10 to 15. So it was too small to be detected by them. They could not detect it. So we still have this threat that if the asteroid, not all asteroids will get detected, in spite of the fact that we have so many sources to actually do it, right? So in 2021, NASA also launched another mission called the Neo Surveyor, again with the same purpose. This is something which they've been very actively involved in. But let's come to something of how can you and me, right, actually contribute to such activity. If you know that there's a threat of asteroids, then how can we actually? I am a professional astronomer, but for example, some of you could be interested in citizen science projects, which actually are involved in doing such things, which very strongly complement the work of an astronomer. So now look at this image over here, right? You can see that here you have a background of stars. And if you look over here, you can see this object moving. I think I told you earlier, I can show you how are asteroids detected. So let's say here you have shots of the sky, right? One, two, three. You have three shots of the sky, and you can see while these stars are stationary, they are in the same positions. You can see this object is moving. And this is an example of a perfect candidate for an asteroid. So, what PanSTARRS does or Catalina survey does is you basically take multiple shots of the same part of the sky. And then in those parts of the sky, you look for objects which move like this. I hope you can see it nicely on your screen. But this object, right? You can see this object which is moving. So the background of stars is stationary, but this object is moving, right? In the center. It's somewhere in the center of the screen. And you can see that that's so there are various citizen science projects, like for example, there's a software called Astrometrica, which you can install on your system. You can participate in this to actually look for asteroids. I also participated. I have a certificate. You can also join in and get the certificate. And if you actually detect such an object, you can report it to the Minor Planet Center, where they then will further do further studies onto that object to actually check. And if this object actually exists, it actually receives a catalog number, and the person who discovered it is the discoverer, and you can actually have the honor of naming the object. Subject, obviously, the International Astronomical Union will support it, and you can do it. So amateurs have also played a lot of role. For example, looking for asteroids. Here's an example of a team of amateur astronomers using just a 6-inch telescope. They actually found that one of the main belt asteroids called Amalthea actually has a companion, a satellite. So this was actually found by amateur astronomers. And like I said, that the Atlas collaboration, this is actually a set of telescopes in Hawaii whose basic job is just to check on these kind of things, right? So let's get back to DART before we wind up. So did the DART mission work? How much energy was transferred? Will it be sufficient to protect the Earth in the case of an asteroid? This is still a difficult question to answer because we still do not know very well the effect of the impact. And so we know that it successfully altered the asteroid's orbit by 32 minutes, shortening 11-hour 55-minute orbit to 11-hour 23 minutes. This was about 25 times greater than what was expected by scientists before they started the mission. So, in principle, it's a successful mission. It has done the job. There's another mission which has been planned, which is called Hera. Hera is going to be launched in 2024 or 2025, and it's going to go back to the same asteroid, Didymos Dimorphos binary, to again observe what is the change in the orbit. For the simple reason, like I told you, that after the impact, the system will take some time to settle down. You also have the Yarkovsky effect. You need to know what exactly has happened, and therefore, the Hera mission will do the follow-up study of the thing to check what's happened. So about 5 years from now, you'll actually have various other things, which CubeSats, etc., which are also planning to further monitor what actually happened with the impact. Have we managed to get a result good enough? right? And but we know what we know is that the bigger the asteroid, right? Bigger the asteroid, the more difficult it's to deflect. But the bigger the asteroid, the more easier it is for you to detect it, right? So in both ways, you have a thing. If it's too big, you can detect it. But if it's too big, you have to deflect it also, right? So that's another thing, right? One some important questions is what's the limiting mass, how does one have to plan the timing if you detect an asteroid, how is the timing, the impact got to be planned, this thing. You can have a look at this website which I showed it to you earlier, which has for near earth objects, it has the catalogs. So we have a good catalog of which are all these near earth objects so that we can do make some plans. And you can actually see, this is the summing up one, that for different diameters, how often do they hit the Earth? 1 meter every 2 weeks, 10 meters every 10 years, 100 meters every 10,000 years, 1,000 meters, that is 1 kilometer, every half of 1 million years. Greater than this is 1 to 300. So that's the expected, this thing. Something like this would cause an effect like Hiroshima, this would be like Chelyabinsk, etc. And that's the kind of effect you could have with these various things, right? So I think we've really come to exciting times where we actually know this threat, the asteroid threat, which we are facing, and we are making some kind of progress in actually planning as to what could we do in case of such a impact. If we know that there's an asteroid coming, how could we do? Probably this kinetic impactor technique seems the most promising one. But like I said, it obviously depends upon the mass of the asteroid. It should, if it's too massive, then you will not be able to deflect it, right? It would be like the case which we did for the earlier one. In that case, in that mission, which was the deep impact one, right? You couldn't push it much because that comet temple was pretty massive, right? So obviously, it would change asteroid by asteroid depending upon which is the asteroid, what's the size, when is the impact supposed to take place, and what exactly we can do for it. But at least the good news is that we are at least progressing in that direction, and we are looking for some kind of solutions, right? So I think we are at least moving in a positive way to protect our planet from this possible kind of disaster. And let's hope we can do that. So thanks a lot. I'll stop with this and I'd be happy to take questions.
Thank you, ma'am, for explaining the entire mission and also the nitty gritty facts about the asteroid and meteoroids. Uh, Now we are open to take questions. We request you to kindly drop in the chat box. So there are some questions, so I'll just highlight those.
Yeah.
Anshita Singh, ma'am, which method is more effective, shifting the orbit of the asteroid or breaking it into the pieces?
Yeah. So thanks, Anshita. But like I told you, it all depends upon what kind of an asteroid it is. For example, if the asteroid is a bit too massive, then even if in that the previous case which I showed you, uh, it depends on how much impact of it you do, and you probably won't be able to get a good enough effect if the asteroid is too massive, right? Then you cannot deflect it. You would have to probably break it into pieces, and then maybe the pieces you could sort it out, right? So probably I would answer that it would depend asteroid basis, depending upon uh, how big is the asteroid, what is the composition of the asteroid, what is it made up of, and how close is it coming to us, right? Like for example, if it is a massive one, but we detect it way in advance, right? Then probably even a small deflection, you know, much earlier will be enough to deflect it away, right? If it's far enough. If it is too close to us, then the deflection you need is much larger so that you save the Earth, right? So it all depends upon the conditions, right, on what you actually detect.
Also, ma'am, would like to know that the citizen science project about the asteroid you were discussing about, basic requirement for that is undergraduate or school students can also
No, no,
participate
no.
in
There
such
are,
things?
yeah. So thanks for bringing that up. I specifically added that so that people can get involved. So actually, you can be as there are many school children who are also participating in that
Yes.
because you basically have to install that Astrometrica software on your machine. Only problem is Astrometrica only works on Windows. It doesn't work on other software. On Linux, you can't do it. You have to do it on a Windows machine. And it's very simple. You have to just see pictures like the ones I showed you. You'll see snapshots, and you basically got to see, is there a moving object? Like the one I showed you in those images, you could clearly see a moving object. So, what you are done is you are every day given new images which you have to inspect and check whether is there any such moving object in those images, right? Which obviously even a school child can also this
Yeah.
thing. Then, when you actually report the things, the procedure is a little bit more tricky how you actually have to give the data that you observe. But if the school student is assisted by somebody, even a high school student probably can manage it on their own. But
Yeah, because many of the schools are having the astronomy clubs and all, and kids are
yes,
really very active in those
yeah, and they're
clubs.
doing it. Many of them are
Yeah.
actually involved in specifically in astrometrica, in asteroid hunting. Because asteroid hunting, the thing is that all these Catalina, Pan stars, all of them have so much of data. They have so much of data that professional astronomers do not have the time to look at all of that, right? And they can easily miss out something. And that is why it was realized that it is very, very important for us to involve citizen science, right? And to involve citizens to actually look for it. So, this is one. There are many more citizen science projects in which people can get involved, in studies of galaxies, exoplanets, various things. And they are, I mean, I've been in touch with many of people who are involved. They're really very happy because, these are people who are interested in science, but they're not professionally trained for it, but they
Yeah.
are very happy to be contributing to it in some form or the other. So do look out for how could you get involved in asteroid hunting. You can Google it, look at it, get in touch with me. I can help you get involved in any of those projects. I think it's good fun to do. And all school kids, I
Yes.
think even a 10-year-old can do it. A 10-year-old maybe is fine.
I think all the young minds who are in the chat right now, in the live right now, I got a little insight about the project ma'am was discussing it. Still, you have any problem, just do let us know. Planetary will be happy to get you all connected with Priya ma'am to get more clarity on this.
Yeah.
Uh, so, some creative astronomer, can you tell some website which give more information about the DART mission?
Okay, so you can the NASA website is there because it's a NASA mission.
Yes,
So the
NASA
first
mission.
place to go to is go to the NASA website and go for DART, and that's that'd be the first hand information. uh, there's a lot of stuff been written about it, lots. But like I mentioned the NASA site because the problem with internet is that anybody can put up anything on the net. So whenever you read information on the net, you need to be a little bit careful about the source. So it is best to go through the standard sources. Like for example, if you go through the NASA dart source, that would be the standard kind of thing. But other than that, if you Google, you'll find many, many, many these things.
Many.
You'll find a lot of
So I
these
think
things.
the official pages are the
That's the
official pages
safest.
of any of
That is the
the
safest
safest.
because the problem is that you still have many non-scientific people who interpret things differently
Exactly.
and may
Interprets.
write
Yes. Yes.
some things which are not true about the mission.
Not true. Yes.
Yeah.
So I think Anshita would like to uh, ask also, ma'am, if we could know the composition, can we create one such? So I really don't understand, Anshita.
What does she mean by Anshita? Do you want to create an asteroid? I didn't understand.
Yeah. So just be a little specific what you want to ask and drop your question again. Meanwhile, I will be highlighting the other.
So we have
So
a lot of
again, yeah.
meteorite samples, right? We have a lot of meteorite samples through which we know what is the different compositions. But I am not too sure about what you mean by creating an asteroid. How small can an asteroid? It can be dust sized.
So
Creative
basically, it's
astronomy.
a dust particle. Yeah.
Yeah. So it can be from dust size to a larger size because, like I mentioned, this is just debris. When the solar system formed, the gas and dust was, coalescing together, and some of the stuff was like left around. So those things could be small, big. It's a whole range. They can be anything. So they could be very small also.
So Vidya is putting, ma'am, can you elaborate about the 2011 mission and its purpose?
Which 20, can you specify which 2011 mission? Uh,
So Vidya, we
could
request you
you?
to kindly be a little specific which mission you are asking for. Yes, ma'am. Asteroid can be created? Question mark. So she is asking, asteroid
Yeah,
can
yeah.
be created on.
No, no, no. But 1 minute, I'm a little confused. Yeah, asteroid can be created. I mean, why would you create an asteroid? An asteroid has to be not on the surface of the Earth, right? This is some
Yes.
object which is sitting, say, between the orbits of Mars and Jupiter or near Earth or whatever. So you can create a thing which has the same composition, fine, but it has more specifications to it, right? Its location essentially.
So I am assuming, like many of the amateur clubs, they have the hands-on experiment to create a comet or something.
Okay, okay.
Probably, I think maybe they are little confused in terms of creating is
Okay.
concerned.
Okay. So the problem to create it is difficult. Why? Because the kind of composition which you have of asteroids is very different from what you have on Earth, right? And therefore, that's how they are identified. So the meteorites which are from outer space, because of their composition, we know that they are most probably do not belong to the Earth. So for you to find the material that belongs to it is so like I showed you, you could have them of carbon, of silicon, of metal. They could be different compositions, right? So I mean, in principle, you can create it, but it's obviously going to make a material which is not so abundant on the earth. So it won't be actually easy for you to make it. Not like the way yeah, comets, but they do that and they get all that, this thing and all that, right? In these demos, right? I think they managed to get a tail and all that, right? Prerna.
Yeah.
When you do
No,
these,
because they also do some experiment with the cold, like ice or something. So I recently
ah,
saw in National Science Center they created a comet. So I am just assuming that
ah,
kids are a little confused with how they created the comet. So probably on the same way in the process, the asteroid is also being created. So I'm
okay,
just presuming that they might think of uh, asking
okay.
this as created means. So
Yeah, so like I
yeah,
say, in
I
principle you can do it, but it won't be like a comet. The thing is, you have a tail and it looks good and all that. In this, there's nothing like that which you're going to get. But yeah, but a shooting star, when it gets into the atmosphere and burns off, that's a shooting star. But
So, ma'am, in connection to the dart only, so probably because as of now we know that it's a success. We've been calling it as a success, like as the trajectory is being changed. But like you had mentioned that we have to wait for some another year, a couple of months to
yeah,
know exactly by sending the other mission to get the more clarity upon the
yeah.
mission success or not. So like on the second mission, like we'll get more clarity, was it a success or
So
not, or
Hera mission is just going to re-observe it, and basically the idea of doing is basically to calculate what is the energy transferred, what's the difference in the thing, so that if I know that I can transfer so much energy by a certain method, then again for the same thing that if I have another asteroid which is coming, then I should know how much of impact. Because I said right, the important thing is you need to calculate what is the how much of impact will happen if you have another asteroid. So this is the thing is basically just to get correct numbers, accurate numbers. How much of energy gets transferred? How much of impact can this actually do? Can it have? So Hera we'll get the better numbers. So if we have a future case, we will know how to plan it, right? If we want to plan a mission like that for some other asteroid, we will
yeah,
get
so
perfect numbers.
this is like a pilot thing to
Yeah.
have
So there's a
as a
certain this thing that we know, okay, for this kind of a asteroid, if we do so much of an impactor, this will be good enough, this will do the job, right? And we basically need to estimate what we need to do.
Yes. So Anshita is writing, okay, ma'am, got it. So she got the clarity on the questions. So we have no more question in the chat box. So I'm assuming that all the online participant got the more clarity upon the mission and also the points Priya ma'am explained during the session. And this video will be available on the YouTube of Nehru Planetarium for further references as well. Even in future, ma'am, if anything related to asteroid, if you're planning, Planetarium will be happy to collaborate, because we have a good network of students from Delhi and NCR, and really enthusiastic ones. So we would like to build a connection between this asteroid hunt thing and the citizen science project. So we would like to circulate the information so that many of the interested can get the benefit of this
Yeah, sure.
citizen
So
science
actually,
project.
if there are students who are interested in getting into this asteroid hunting thing, do let me know. I will get you in touch with people who are actually actively involved in that. There are people
So
involved in that.
definitely, definitely, ma'am. And thank you once again for coming with us and discussing such an important mission and giving more clarity and depth understanding on this. So
Yeah,
good afternoon and thank you.
yeah. Thanks so much. Thanks so much for having
Thank
me.
you.
Thank you.
Thank you. Thank you, everyone. Thank you for joining in. So we'll really hope to see you again for some another session of the live at the Nehru Planetarium YouTube live. Thank you. Bye and take care.
Bye bye.